So in last class, we went and we derived these two equations of motion. This is for the elastic, or the pendulum with an elastic wire. So pendulum connected to a spring with an angle theta, and then we measured the stretch in that spring with RT. And so we attempted to linearize this, but we ended up still with a nonlinear equation. So I went back and I checked what we did wrong, and for this problem we do need to assume small motions. In this case we'll recast R as epsilon times R. Theta is equal to then epsilon times theta, and here epsilon is much less than 1. So epsilon is a very small parameter. And then this just then propagates down into the derivatives, and then you go and you plug this into the equations of motion, and you can group them up into terms of things multiplied by epsilon, things multiplied by epsilon squared, and things multiplied by epsilon cubed. Anything multiplied by epsilon ends up being our linear equation, and everything else is nonlinear in this regard. And we can also do some simplification to the cosine and sine terms. And then by doing this process, we end up with a pair of decoupled equations of motion, one for the rotation of the pendulum and one for the radial translation of it. I'm going to post these notes on Canvas, so you don't need to worry about writing them down.
Why are we eliminating some? Like, why are we able to assume small motion?
So it restricts you to, you're adding a constraint to the physics of the problem. You're saying that the vibrations or the motion of the system are going to be restricted to a small domain. And so that implies that if this thing is being excited by an external force, that the external force is also small as well. That's what we're implying here. And so things like this pendulum doing a full 2 pi rotations is not allowed. That's all. So, things like if you perturb the system and you want to give it some initial displacement, let's say angular, this is too much. 90 degrees is too much. If something like 4 degrees, that's an acceptable initial condition. So we're restricting the domain on which our problem is valid for. By doing that, we then end up with a set of linear equations, which makes life easy because we can solve these, and there's no coupling, so it's even easier to solve these than if there was coupling between them. However, if you want to study, the full response for any set of initial conditions or any applied force, you've got to use the full nonlinear equations, which may not have an analytical solution. Probably for this case, it does not have an analytical solution, I would imagine. And then it gives rise to things like chaos and chaotic behaviors and a whole bunch of other very interesting nonlinear features that are just out of scope for this course. Like I said, I'm going to post this on Canvas, so don't feel rushed to write it down. And with that, we're going to move on to momentum. We're going to go through linear and angular momentum, and then we're going to see the angular form of Newton's second law. And we'll come back to momentum in 2 weeks when we deal with impulse momentum theory. Okay, so the product of the mass times the velocity vector is simply called the linear momentum of the particle. And we're going to define the linear momentum to be capital L, and this is just simply equal to mass times the velocity. With that in mind, Newton's second law can then be written as being that the sum of the forces, the vector forces, is equal to the vector L dot. And in this case, this is the rate of change of the linear momentum. Or we can also say here that the sum of the forces is equal to the mass times the velocity dotted, or the time derivative of the velocity, which we now know is the acceleration of the particle. And if no forces are acting on the particle, then linear momentum is conserved. And this is really all we're going to say right now about linear momentum. We will come back to it in 2 weeks when we deal with impulse momentum theory. All right. In that case, we're going to move on and talk about angular momentum, and this is for particles we're dealing with right now. We're going to define the angular momentum, h, capital H, it's a vector. We're going to add a subscript O here, so this is the angular momentum about the origin for the particle, wherever your origin is. It's going to be equal to the position vector crossed with the linear momentum, or the mass times the velocity, or if we are using dots for derivatives, we'll get h0 equal to r crossed with m r dot. And we can now use this to express Newton's second law in terms of sum of moments. So in this case, we'll have that the sum of the moments about the origin is equal to the rate of change of the angular momentum. And since we've got a cross product in the definition for the angular momentum, we're going to have to go and do a product rule when we take this derivative. So this h sub o dot, this is going to be equal to r dot crossed with m r dot plus r crossed with m r double dot. What is the cross product of a vector crossed with itself? What is that equal to? Some people are like, I have no idea. It's 0. By definition, the cross product of a vector, even if it's scaled by some scalar, it's going to be 0. So this is going to go to 0, and we're left with that the rate of change of the angular momentum is equal to r crossed with m r double dot. So this is angular momentum for a particle. And this will take into account things like parallel axis theorem as well. It's built in there. Okay, any questions? Okay, if not, we're going to do a quick example and then we'll go on to doing the worksheet. So we're just going to apply this angular momentum theory, or the angular form of Newton's second law, to a pendulum. You've seen this before, or at least a form of a pendulum using the translational form of Newton's second law. We're going to go ahead and do it for the angular form. We're going to assume in-plane oscillations, that the string is massless and also inextensible. There's no friction or dissipation, so no air resistance or anything like that. No friction where that string is connected. And we're going to determine the equation of motion using the angular form of Newton's second law. We're going to begin by starting with a coordinate system. We're going to put our origin at the point of rotation, and in this case, we're going to use polar coordinates. Although you don't have to use polar coordinates, you can still use Cartesian if you want. But polar will drastically simplify the analysis. That's our e hat r, e hat theta. We're going to use here polar coordinates. And polar coordinates is best used when you've got rotation about a single fixed point, which is what we have here, and that's why we're going to use it here. For position vector, we're going to draw from the origin to our particle. We'll say that this is our r vector, and then the r vector, which is a function of time, is equal to L e hat r. L is a constant, but e hat r is not a constant. E hat r is changing with time, and therefore the position vector is also a function of time. It says here we're going to compute velocity and position vectors. That should actually say acceleration. We're going to compute velocity and acceleration vectors. We already have the position vector. We just take the time derivative, and this is going to be equal to r. R dot is equal to L dot e hat r plus L theta dot e hat theta. I said L was a constant, so that first term will be 0, such that the velocity vector r dot is equal to L theta dot E hat theta. And you can also just find this from the formula that we've discussed or derived for velocity and polar coordinates. We'll go take another derivative to get the acceleration. In this case, we're going to get minus L theta dot squared E hat r plus L theta double dot E hat theta. And I just skipped the L dot terms here. Okay. All right, so in order to apply Newton's second law, we're going to need a free body diagram. So we're just going to go ahead and draw one right here. Here's our particle. We've got gravity pulling down. That's mg. We've got some tension pulling in the E hat r direction. We're going to go and decompose the gravitational force into components, with this angle here being theta. That will be mg cosine theta. This will be mg sine theta. Okay, we're going to apply Newton's second law using the angular form. So we'll have the sum of the moments about our origin is equal to the rate of change of the angular momentum. So first, sum of the moments, just as a reminder, is equal to the sum of the cross product between the position vector and the forces. And we said earlier that h dot 0 is equal to r crossed with m r double dot. So let's go and compute the angular momentum first. This is going to be equal to, well, our position vector is L E hat r crossed with the scalar m times our acceleration vector, which is minus L theta dot squared E hat r plus L theta double dot E hat theta. Whenever I do cross products, I like to use what I call the clock. And this is where you'll write your unit vectors in a circle, and we'll use E hat z for the third direction. And in this circle, going clockwise gives you a positive output from a cross product. So E hat r crossed with E hat theta will give you positive E hat z. If you do E hat theta crossed with E hat r, you'll get a negative E hat z. And if you're working in Cartesian, this is I, j, k. Like that. Okay, so we have first E hat r crossed with E hat r. That is going to be 0 by definition of the cross product. So we won't have any E hat r, any term from that. And then we have E hat r crossed with E hat theta. That will give us a positive E hat z. And so we'll find here that the rate of change of the angular momentum is going to be equal to, we'll get ml L squared theta double dot, and this will be in the E hat z direction. All right, we said that the sum of the moments is equal to the sum of the cross product of the position and the forces. And so in this case, we're going to get L E hat R, that's our position vector, crossed with the forces here, which will be, if we go back to our free body diagram, we will have in the E hat R direction, we're going to have T minus mg cosine theta E hat R, and then minus mg sine theta E hat theta. And let's add a moment, an external moment to this system. So if we come back up here, let's just say that there's some external moment, m of t, acting on the system. Yeah.
What's the H here?
The h is the angular momentum, which we defined as r cross mr dot. So we're just going to add our external moment here. And you can imagine that there's like a motor or something at the origin driving this pendulum, and that's what's creating this moment. Or there's maybe some external wind force or something causing this thing to move. Or maybe the platform that it's connected to itself is doing something weird. So in that case, the moment acts in the E hat Z direction because it's rotating about the E hat Z direction. So we're going to add in here our moment, m of t E hat Z. So the sum of the moments about our origin are going to be equal to, well, E hat R crossed with E hat R is 0. So we'll skip the entire first term, meaning we don't need to worry about the tension when we're dealing with this problem. We'll then go E hat R cross E hat theta. That will give us a positive E hat Z. So we're going to get here m of t minus mg L cosine theta. Oh, whoops, not cosine theta. That should be sine theta. All of that in the E hat Z direction. Then we can combine the H0 dot with the sum of the moments, and we'll find that we get m of t, m of t minus mgl sine theta, the E hat Z direction is equal to ml squared theta double dot E hat Z. And then from here, we'll find that ml squared theta double dot plus mgl sine theta is equal to our external moment. Or we can simplify and we'll get theta double dot plus g over L sine theta is equal to the moment m of t. And that is our equation of motion. Yeah,
Do you need to divide M of T by like
you do.
ML?
Yeah, hold on. Yeah. I'm missing that. Okay. Any questions on this before we move on to the worksheet? So for particles, we're always going to take some of the moments about the origin. When we go to rigid bodies, we will be taking some of the moments about different points on the body, depending on what we're trying to find. But generally, it will always be about a point of rotation, which may be the center of mass, may not be the center of mass. It depends on the problem. Yeah?
Should that be 1/ml squared?
Yes. Okay. Any other questions?